Hello, and welcome back to EECS 367, Introduction to Autonomous Robotics, and Robotics 320, Robot Operating Systems. This is our second lecture of the semester. The topic for today's lecture is on path planning. So that is, how can a robot efficiently calculate a path from some given point A, which could be a start location, to a given point B, which could be a goal location. So to start today's lecture, we're going to be looking at some concrete examples of real robotic systems that depend on path planning. And so in this first set of examples, we'll be looking at robots from RoboCup. So RoboCup is a fairly famous competition from the robotics community where teams of robots compete against each other in soccer. So in this particular video here, we'll be looking at the team of robots from Carnegie Mellon University competing in a 5 versus 5 game of soccer as they try to score a goal. So the first thing to note is each of the robots is propelled by a set of wheels underneath the base of the robot and has a motorized actuator, as shown here with the kick, that allows it to essentially kick the ball as a projectile. And so a few things to note here. First of all, is these robots are extremely fast. So the computation on board is able to keep up with the rapid pace of the game and lead to some really impressive athletics as shown in that last goal. And so if we look under the hood of these robots, they're really pretty impressive systems because of course each individual robot has to handle not only the controls and the sensing on board for its individual unit, but on top of that, there's coordination between the team so that each unit can communicate to its neighbors, to its teammates, and then coordinate a plan, a strategy for trying to achieve a goal, right? Meaning like an actual soccer goal. And so within that, one of the crucial steps of strategizing is planning out a path for each of the individual robots to take. And so it's really crucial that all of those steps, including the path planning, are efficient if the team is going to be able to perform a successful strategy. Because as we saw in that last clip, and as we'll see coming up, the pace of these games is really, really impressively fast. So to demonstrate another example of how, kind of impressive the strategy that comes from these robots is, in this clip, it's going to show the orange arrows show the passing that's going to occur. And then the blue arrows show the strategized motion, the sort of strategized path plan that the receiving robot has to take in order to successfully receive the path. And so again, it's a demonstration of how really important path planning is within these RoboCup teams, and how it's really crucial that the path planning is efficient if it's going to be able to keep up with the game. So in this case, it's another case of kind of impressive multi-step passing and strategizing in order to achieve a goal. And so another thing that's quite impressive about these robots is they're actually able to overcome slight kind of miscalculations or sort of unintended actions, right? So that first example was a shot on goal, but you can see the robots quickly recover and are able to recalculate their strategy, recalculate their paths, and ultimately achieve a goal, or coming up, I think it should be a goal. Let's see. There we go. And so another thing to point out, which is, from roboticists, that's really impressive, is that these video clips here are shown at, you can see it shown in the lower right-hand side, 0.5 times speed, meaning these video clips are slowed down as compared to what you would see if you were an observer in the live event. So in other words, these robots are moving faster in real life than they appear on screen. That's notable because in research, one of the common things you'll see when you see robotic research papers and demos is usually, I'm painting with a broad brush here, but usually the videos are sped up because our robots typically operate much slower than a human observer is willing to sort of sit and watch. So again, that's just a testament to how impressive these teams in RoboCup are, and in this particular case, the team from Carnegie Mellon. Another kind of slightly funny thing we could point out in this particular case is that you might have noticed that one of the robots in the early portion of the clip sort of fell over amid a collision, and so it's it's kind of an interesting case of perhaps art imitating life. If you follow modern soccer, there's some controversy around that. So if you're interested in RoboCup, I would certainly recommend reading about the history of RoboCup, because the competition still goes on. So it was started in 1997 was the first competition, and even today there's annual competitions involving these soccer playing robots. And so if you're interested, like I said, I would encourage you to read the history, and in particular, there's a very famous roboticist named Professor Manuela Veloso from Carnegie Mellon, who was one of the sort of champions of RoboCup, in addition to all of a number of other really, really exciting and interesting research topics that she pioneered. So if you're interested, this is one particular article that's interesting and worth reading. So another project that's exciting that has come from Professor Veloso's lab that also uses path planning is a project by the name of cobots. So shown here are a set of these cobots, which essentially serve as somewhat like autonomous tour guides within the Carnegie Mellon robotics building. So for example, on this next slide, you'll see a video clip of these robots navigating autonomously through the building using path planning. And so what these robots were able to do is they could interact with human visitors. You can see they have display screens which they could relay information, as well as cameras that they could use to perceive the humans that they were interacting with. Right, so they could provide directions or sort of other kind of tour guide like interactions with humans. And so once again, beneath the hood, what these systems are doing is they're running path planning efficiently on top of the other sensing and control mechanisms. So if we look sort of under the hood at how these systems are able to do this, they essentially build up a map of their environment, and then using that known map of their environment, they're able to plan these paths. And so it's notable that this project, in the years that it was running, it really achieved a pretty impressive set of statistics about how far these robots were actually traveling. So even just within the buildings themselves, over the course of shown here in this figure, 3 years, these robots ultimately traveled over 1,000 kilometers, autonomously. So this is, again, a really kind of exciting case of how path planning autonomously can, while it might seem somewhat simple in certain cases, it adds up to a very, very impressive system when it's allowed to execute autonomously over time. And so another case of this particular cobot project. So what's shown here is the robot performing both localization and planning. So on the left-hand side, what you're seeing in those red circles are the set of sort of hypothesized poses of the robot in the space of the map. And then as the robot moves, you can see it becomes more confident about where it is within the map as it's simultaneously planning a trajectory and executing on that planned trajectory. On the right-hand side, then, we're shown the sensor input that the robot was using to localize itself, which, again, is an interesting topic which we can look at further in this course. So that then brings us to our Project 1 and what it is that we're going to be focusing on as we start to work on Project 1. So in particular, what we're going to be doing is looking at path planning. And so the particular algorithm for path planning that we'll be focusing on is what's known as A-star planning. And so A-star is a search algorithm which we'll be applying in a 2D world similar to the one shown on the slide here on the right-hand side, where our algorithm will ultimately be implemented in a combination of JavaScript and HTML. So it'll be viewable within a web browser. And the kind of base data structure that we'll be using for this algorithm is what's referred to as a heap data structure. And so this heap data structure is what will maintain a priority queue for the A-star algorithm. And so the details of this heap data structure and how a priority queue is used within A-star will be covered later on in this lecture. And so one other reminder about this project is just to remember that you'll be submitting your code through your GitHub repository. which we talked about in lab on last Friday's on last Friday's lab section. So with this project in mind, let's consider where path planning fits in a general robotic framework. So to do that, let's first note that path planning assumes the robot has access to three key pieces of information. The first is that the robot must know where it is within the environment. And so this is what's referred to as localization. Next, before the robot can calculate a path, it needs to know where the path should lead to. So in other words, the robot needs to know some goal location that it would like to move towards. And then finally, the robot should have access to a map of the environment, which includes possible positions or configurations where the robot would be colliding with portions of the environment. And so if the robot has access to these three pieces of information, it should be able to calculate a collision-free path, right? So a kind of collision-free sequence of positions in configuration space where the robot would not collide with the environment and arrive at the goal location. So the first piece of this, right, the first piece of information that the robot needs to have access to is this localization information and the map information. And so a really cool example of how the robot could acquire these two pieces of information comes from a fellow student from the Laboratory for Progress. So Alphonsus Adubradu made a really cool demonstration of localization and mapping, which could feed into a path planner, as demonstrated in this video here. So before I play it, the left-hand side of the screen is going to show an aerial view of the sensor information of a fetch robot that's operating within this simulated home environment, which is shown then on the right-hand side. So the sensor that the robot has access to is what's called a LiDAR scanner. So this particular sensor essentially shoots out a set of laser ranges in front of the robot, which return then the distances of collisions of those lasers with from the robot sensor itself. And so as the robot then moves within the environment, what you'll see is, and I'll start playing the video now, what you'll see is the robot will coalesce these sensor measurements to form essentially an occupancy grid that represents a map of the environment. And so while this robot is simultaneously creating this map, it's also able to localize the position of the robot, which is shown on the left-hand screen there. So this, using this information that the robot is generating, it could then feed this created map and this known localization into a path planner, right? And so on this second video, Alphonsus then implemented a path planner using the synthesized map and known localization by using user input, which is shown in the green arrow as he clicks in different portions of the map, which you'll see in a moment here, to provide the goal location. So as Alphonsus clicks, the robot then is able to navigate to those desired goal locations using path planning. And so this particular demonstration here is really not too dissimilar to what we're going to be implementing in this course, but simply with the fact that we're going to be assuming that the robot has a known map. So we're not going to be performing the localization and mapping component. All right. So at a high level, right, path planning is essentially this question of how do we get from point A to point B, right, where point A is the known localized initial position of the robot, and point B is this desired goal location of the robot. So let's go back to robot soccer and consider how path planning can actually be implemented. So in particular, here's an image from a set of robots that Professor Jenkins worked on when he was on faculty at Brown University. And so if we look at them a little bit more closely, what you might notice is that these are actually iRobot creates that have been modified to make them capable of playing robot soccer. And so really these iRobot creates are very similar to the Roomba sort of vacuum cleaning robots that you may have seen. The only difference is that instead of having a vacuum cleaner, these robots have been modified to have relatively high powered computers that can perform the control and perception tasks. And so the way that these robots were implemented is that they first had the capability of localizing themselves within the playing field using an overhead camera with AR tags on top of each of the robots. And so this is then what would allow the robots to be positioned within the control system on a map of the soccer field. And so if we look at this map, it's a 2D space that contains the positions of each of the robots within the soccer field. And so for our purposes of planning, one way that we can think about this soccer field is as a grid, a sort of discrete grid of cells that represent the possible poses of robots across the field, right? And so if we think about this grid of cells then as a graph where there's local adjacent connections, then what we could do is we could consider each edge along this graph to represent the distance that the robot would have to travel to move from one cell to the next. And so the nice part about using this representation for the space of possible poses, which in the future we'll refer to as configuration space, is that it allows us to very nicely and kind of cleanly represent possible collisions. So in particular, any of the cells where the robot would be in collision, we can consider those sort of invalid poses that the robot can't take for the purposes of planning. So using this representation for state space and collisions, then the question of path planning can be boiled down to how can the robot find a sequence within this graph that will take it from its known start location where it's been localized to its desired goal location somewhere else within the soccer field. And so there's a number of different algorithms, a number of different approaches that could be used to approach this motion planning problem. Some rudimentary algorithms, which we'll talk about later in the semester, would be what are referred to as the bug algorithms. So we have a lecture later in the semester that'll be dedicated to these algorithms. But for today's lecture, for the remaining of today's lecture, we're going to be talking about graph search and how a set of algorithms from this subfield of graph search can be used and applied to the problem of motion planning. So the set of algorithms that we're going to be looking at today are the ones highlighted in the second bullet here. So these are depth-first search, breadth-first search, Dijkstra's algorithm, the A-star search algorithm, and finally greedy best fit first search. So this is what the core of today's lecture is going to be on, but this won't cover all of motion planning. So there's a number of additional approaches to motion planning, some of which we'll cover in later lectures. So later on in the semester, we'll look at sampling-based search, so algorithms like probabilistic roadmaps or rapidly exploring random trees. And in addition, there's another set of approaches that are optimization-based instead of search-based. So this would be using techniques like gradient descent and potential fields in order to represent how the robot can move through space to satisfy a goal configuration. So to start with, for the rest of today's lecture, we're going to be focusing on these fixed graph search algorithms. And so to start our discussion, let's first consider a simple search graph. And so when we say a simple search graph, what we're referring to is a set of nodes distributed over space where these nodes end up comprising a graph. So there's a set of nodes, and in addition, there's a set of edges that connect these nodes. All right, so each node represents the potential pose of a robot in space. And the edges then between these poses denote that the robot could transition from one pose from configuration space to another pose in configuration space without any collision in between. And so in addition, since there's a physical sort of actuation associated with moving from one pose to another, we could associate a cost to each edge. So these costs denote essentially how expensive or potentially how long it will take for the robot to transition from one pose to another along a particular path. So then for the purposes of our search algorithms, what we'll consider is that each node within this search graph maintains the distance that's required for the robot to travel from the start position to that particular node within the graph as an integer scalar cost. So you can see initially the start goal, of course, has zero cost associated with it, since there's no distance that the robot needs to travel to go from the start node to the start node, whereas all of the other nodes within the graph, which have not been essentially operated on by any particular search algorithm yet, start with this term of infinite cost. And so in addition to this, one other notation we can use is we can represent the parent node of each of the nodes within the graph, representing the route that the robot would have taken from the start node to reach that particular node in a sort of optimal or sort of minimized cost fashion. So for example, the parent node of the first node that has a cost of 0 plus 5, just directly above the start node, its parent node is the start node, and it has a cost of 0 plus 5, which is 5, because that's the total cost it would have taken if the robot had started at the start node and traveled to the 0 plus 5 node. So using this representation of configuration space, this is going to be sort of the foundational data structure that our search algorithms will be using as they try and calculate a path through configuration space from some desired or from some known start location to some desired goal state. And so the first algorithm that we're going to be looking at is what's called depth first search. And so to start with, we'll have we'll start with just sort of an intuition. So we'll sort of step through the algorithm without any code, just looking at kind of conceptually how it will operate, and then after that we'll take a look at pseudocode and sort of build up from there. So to start with, so if we go back to our soccer example, so we have here two poses for the robot. So in the lower right hand corner is let's say the known start location of the robot, and in the upper left hand corner, that's the goal location. So that's where we want our path planning algorithm to ultimately move the robot towards. So the way that we can represent these positions is with respect to the global frame of the soccer field, where the soccer field, the map of the soccer field becomes a frame of reference. And we then have two configurations. We have the initial configuration and the goal configuration, represented as the 2D vectors in this two-dimensional space, with respect to that global origin, which is in the lower left-hand corner. So with these initial and goal configurations, then what we can do is we can represent the space, this 2D soccer field, as a graph, which is a discrete array of cells. So each cell could be indexed by a row and a column. Each of the cells have some known epsilon length, and the 2D center location of each cell can be then sort of mapped to a 2D position in the world coordinate frame, or in this global soccer field map. So one question then that we should maybe start with is, given some robot pose, whether it's the goal pose or the initial pose or some intermediate pose, what happens if the robot pose doesn't exactly overlap with the center of a cell? Which cell should it be aligned to? Because of course this pose in the two-dimensional soccer field case is a pair of continuous variables, right? You've got the x coordinate and the y coordinate, whereas our graph is discretized. So to look at that a little bit more closely, let's consider this question of graph accessibility. So in particular, you might be asking, well, what happens if the continuous robot pose, like the xy coordinates, is not directly on top of the center of a grid cell? Well, in that case, you'd have to consider that these grid cells represent a space, a region of the configuration space that's within the epsilon step away from the center of the graph node. So another way of sort of saying that is that each graph node represents any of the continuous poses that are most closely positioned to that center of the graph node, right? So in this particular example, in this particular case here, X would be the center of this cell, and the configuration Q would still be represented by the graph node at center point X, because Q is within this bounding box region that's represented by the graph node X. So with this sort of framework in mind, now let's step through an example of depth-first search in this soccer field example. So in particular, let's say that the start node is represented in the lower right-hand corner by the purple graph node, and the goal node is in the upper left-hand corner at the orange graph node. So to start depth-first search, so as the name suggests, the way depth-first search is going to work is it's going to sort of be initialized at this starting node in the graph, and it's going to iteratively search through the graph in the direction in a direction pre-specified until either it reaches the goal node or it runs into some collision. Right, so it's going to continually search in a depth-first fashion. So let's step through sort of iteration by iteration and look how this is going to work. So starting at the start node, the first thing that depth-first search will do is it'll assign a distance of 0 to that node in the graph. Okay, so this again this distance is to represent the idea that the robot would have to travel 0 units to arrive at this start node, because again it is initialized at the start node. After this, what depth-first search will do is it'll consider the adjacent nodes of this first visited start node to be in what's called the visit list. And so the order in which these nodes are added to the visit list has to be predefined. So for this particular example, we'll consider adding the adjacent nodes to each visited node in the order given by like east, south, west, north. So in this case, east is on the right-hand side of the screen, which is the neighboring node here indicated by the number 1. South is outside of the soccer field, so we don't add any nodes to the visit list. West is to the left-hand side of the visited node, the start node, so that's indicated by the number 2. And then north is directly above the start node at node 3. So we have our start node, which has been visited, and then we have these 3 adjacent neighboring nodes now added to the visit list. So for each of these neighbor nodes, the depth-first search will then ask the question, if the currently visited node, which at the current iteration is the start node, if that were to become the parent of the adjacent neighbor's node, would the path distance associated with those neighboring nodes become back to the start node be shorter than the distance is currently defined? So if you remember how we set up our graph data structure on a few slides ago, we said that all the nodes would be initialized with a distance of infinity as a sentinel value. So at this point now, and then within this check, if the value of the distance for each of the adjacent neighbor nodes would be shorter than it currently is, if this currently visited node was considered the parent of the neighbor nodes, then update the parent of those neighbor nodes to be the currently visited node. And so in this case, we can see since all of these adjacent neighboring nodes have not been considered previously, their initialized value is infinity. And so the distance that would be traveled from the currently visited node to those adjacent nodes has a distance of 1, right? So 1 step away. We can see that the distance of 1 is indeed less than the initialized value of infinity. So we'll update the neighbor nodes' distances to all be 1 and assign the parent node of those adjacent neighbor nodes to be this initial start node. At that point then, the depth-first search will choose to visit whichever of the neighbor nodes has the smallest travel cost associated with it, and it'll in cases of ties like shown here, where all the neighbor nodes have the same cost to travel, it'll pick one of the values from the visit list based on a predefined order. So for depth-first search, that would be the most recently added node to the visit list, which in this case is node 3, directly above the start node. So now we consider this node 3 to be the visited node, and so we'll mark this node as visited, and we'll then move to the next iteration of the depth first search algorithm, which will repeat this process over again. So at the second iteration, we're going to add the adjacent nodes of the currently visited node to the visit list. So this is going to be nodes 3, 4, and 5. And then we're going to again run the check of whether considering the currently visited node as these nodes' parent would in fact lead to a shorter path back to the start for these neighbor nodes. So in this case, the path back to the start for these neighboring nodes would each be 2 steps. So it'd be 1 step to get to the currently visited node marked X, and then 1 additional step to get from node X back to the start node. So that's why the adjacent neighbors in this case have a value now of 2 associated with them. So in this case, once again, now we're going to consider which node should be visited next. We can see that the three nodes in the visit list here all have equal cost back to the start node. So it'll pick the node to the north of node X, or to the north of this previously visited node, based on the predefined order, and then it'll move to the next iteration. So once again, it'll say, okay, currently we're visiting the node, the second node marked X, and we're going to consider each of the adjacent neighbors to be in the visit list. But to make this problem more interesting, let's consider the case where there's actually a collision that could occur, as marked by the blue rectangle here. So in the case of a collision, what depth first search will do is it'll identify that one of the neighboring nodes is invalid. It would result in a collision. So when it identifies that, it'll decide not to add that neighbor node to the visit list. So in this particular case, node 7 has that red X crossed out to indicate that it would not be added to the visit list during this iteration of the graph search. Instead, what we'd be left with is the visit list of just node 5 and node 6 to consider. And so based on the visit list, the next node that would be chosen for visiting is the node that was most recently added, which in this case is the node marked with the square number 6. And so we would then visit that node and continue on to the next iteration, where again the adjacent neighbors of that node would be added to this growing visit list, but with the caveat that any of the neighbors of the currently visited node that are either in collision or that have already been visited or queued in the visit list would not be added or sort of duplicated a second time. So in this case, the only new node that's added to the visit list is the node marked with the square 6, so the sort of 6th node within the current visit list. So once again, we would then continue to the next iteration where we choose to visit the most recently added node of our visit list, expand that node by adding its neighbors to the visit list, and then we continue this process, right, of expansion and visiting new nodes and expanding on the visited new nodes and so forth, again using that predefined order for choosing which nodes to visit. And finally, then, we would have reached the goal node. So at this point, you can see one of the nodes within the visit list, which is chosen to be visited next, is in fact the goal node. At that point, the depth first search would identify that the goal node has been visited, and then decide to conclude the search, noting that a path had been found. And so once it concludes the search, what it can do is it can then sort of trace back its path through the subset of the graph that has been visited, which is guaranteed to have a sequence of steps from the initial pose to the goal pose. And so that then would conclude this depth first search walkthrough. So now that we've stepped through it, kind of iteration by iteration in this visual format, let's now turn and try and convert this idea into some pseudocode that you could then use if you wanted to implement this algorithm. So for this, I know this is a big block of code, but we're gonna step through it in sections. What we're looking at here is pseudocode for what we call this search algorithm template. So we're going to use this template pseudocode for the remaining sections of the lecture, where it'll be used to represent each of the different search algorithms that we consider, simply by sort of swapping out key pieces of code, or kind of key lines of code for each of the algorithms. So within this template, if we step through it, the first portion is really sort of initializing the variables that will be used for the search algorithm itself. So to start with, what the first line of code is doing is it's saying, let's create this each node variable, so that each node has a distance set to infinity as a sort of sentinel value. It has no parent node for the to start with, and then in addition, it has not been visited as to start with. After we've initialized all the nodes, we then initialize this, or sort of update the specific start node. So for the start node, right, we said that its distance would be set to 0. So this is in the second line of the pseudocode. Its parent would be none, because it has no parent since it's the initial starting node. But it has been visited, since that's the initial sort of node that will be visited as the algorithm begins to iterate. And then to finally initialize our visit list, we're going to initialize it simply with the start node. So that will ensure that the start node is expanded or visited to start the algorithm, right? So with that, then the next portion of the pseudocode is specifying the main loop of the search algorithm, which we step through. So within the main loop, what it will do is it will first check if either the visit list essentially has elements that are left to be visited, and also if the current node is not the goal node. So if either of these conditions were true, so that is, if the visit list were empty, or if the current node was the goal node, then the search would be done, because either it would have found the goal, or would be left with no more nodes to visit. So in this case, as long as both of these conditions are false, it knows that there's still work that's left to be done. And so the first step within each of the iterations, as we walked through the algorithm, is it has to decide from the visit list which node should it visit next. And so in the line directly below the while loop, what we're doing is we're taking the current node that we're going to be visiting to be the highest priority node from our visit list. And so we'll look at how to define highest priority for depth first search. But once you've done that, once you've found the node to be visited as the highest priority node from our visit list, the next line of code then sets that current node to have been visited. So it sets the visited property of that node to be true. Next, the key step in this next portion is to add all of the unvisited neighbors of the current node that has been visited to the visit list. So the visit list will be growing, as we saw in the visual example, and then to assign the current node as a parent to each of its neighbors if it has that sort of shortest root property that we discussed. And so that's what these key lines of pseudocode are expressing. Finally, then, after the search loop has concluded, so either it ran out of nodes to expand, to visit, or it found the goal node, the final step then is to output the resulting route, right? So the resulting path that can be taken by the robot, and also the path distance that the robot should expect for it to travel from the initial position to the goal position. So given this initial search algorithm template, let's now look at what we would have to change within this template to express the depth first search algorithm specifically. So in particular, so if we go back to our search template, now let's highlight the portions of this template that we could change to make specifically implement depth first search. And so highlighted here on this slide are the key changes we would make to implement depth first search. So in particular, the primary substitution that we're making is we're just going to be expressing our visit list as a stack. So a stack is a data structure which it's similar to a list, except that it expresses it sort of nicely expresses our notion of highest priority as being the most recently added element. So in particular, this stack you could think of like one kind of mental model or conceptual model that's I've heard referred to is think about it like a stack of pancakes, right? So the idea is that you can kind of keep adding elements to the top of the stack, and as you do so, the stack keeps growing, but you never remove elements that are not on the top of the stack, right? So you'd always take off the first pancake. You wouldn't, because you don't want to topple over this sort of tower, right? So you would sort of add elements to the top and take off elements from the top one by one. And so in pseudocode, the way that that's expressed, that notion of removing the element with the highest priority is with the pop operation. So you'd pop the top element off of the stack to give you the node in our graph, which was most recently added to the visit stack. Similarly, when you're adding elements to the stack, shown in the line with underneath the for loop is a push operation. So every time that we're adding nodes to our visit stack, we're pushing them to the top of the stack. So with that, all the remaining portions of our search template can remain the same. But with this pseudocode here, we've implemented depth first search in the same fashion as we showed through our iterative walkthrough. And so to look a little bit more at this stack data structure in case you have questions, so a stack is referred to as last in, first out data structure. So this is abbreviated LIFO, a LIFO structure. And so the two operations that are supported for inserting or removing elements are called push to add an element to the top of the stack, and pop to remove an element from, again, the top of the stack. So illustrated graphically here in the top row of this graphic is showing a sequence of push operations, and so you can see the stack iteratively grows, and then in the second row of this figure are a sequence of pop operations where, again, each time only the top element from the stack is removed, and the resulting stack grows smaller each time. So with this background, you might be wondering then, what would this depth first search algorithm look like within our 2D search canvas template for project 1? And so to give you some idea, so here is an example of what you should expect once you've implemented, or if you choose to implement, I should say, depth first search within the search canvas, because it's not a required feature for this course. But optionally, if you're interested, you can implement it within the code stencil. And so you would expect to see behavior something like this, where, again, based on that kind of strict ordering of how depth first search chooses to expand and visit nodes, you sometimes can result in these very zigzagged paths. But notably, it does find a valid path, valid meaning there's no collisions with the environment, that takes the robot from the start node, as indicated by the dark blue square towards the upper left portion of the map, to the goal node, which is the green square in the lower right portion of the map. All right, and so now that we've looked at depth first search, so the next algorithm that we're going to look at is very similar. It's what's called breadth first search. And so to look at this algorithm, we're not going to go through the visual walkthrough, although if you'd like to do that, it's a good exercise to sort of work through that on paper, or if you're interested, you can come to office hours and we can talk through it in person. But for the sake of time, one thing that we can do is we can go back to our generic search algorithm template and ask what would we have to change to take this template and implement breadth first search. So the key distinction between depth first search and breadth first search is essentially what data structure you use to represent the visit list and how you define priority with respect to that visit list. And so unlike depth first search, which uses a stack data structure, you can implement breadth first search using a visit queue to represent what we had been referring to as the visit list. And so with this visit queue data structure, the only substitution you have to make is simply replace that visit list with the visit queue, and then when you decide at each iteration of the main search loop which node to visit, you would perform a dequeue operation, and then every time you're adding one of the neighbor nodes to the visit queue, you would enqueue the node. So to provide some additional details of the queue data structure, let's look at this next slide, which summarizes the key kind of idea and distinction between the queue and the stack. So a queue is what's referred to as a first in, first out, or you'll sometimes hear it abbreviated as a FIFO data structure. And so similar to the stack, there's two operations that are supported. These are referred to as enqueue, where you add an element to the back of the data structure, and dequeue or dec, where you remove an element from the front of the data structure. And so really the key distinction between the queue and the stack is in the queue, this insertion of elements and the removal of elements happen at kind of opposite ends of the data structure as opposed to occurring at the same end. And so if we look at how breadth first search using this queue data structure would perform in your search canvas, here is some output that you should expect to see if you were to choose to implement breadth first search. And so notably, unlike depth first search, we don't observe in this case that the plan produced has that very up and down kind of zigzagging behavior. So it is much improved. However, there's no guarantee that it has found the shortest path. And so the next question to ask is there some way we could modify these algorithms to ensure that we're able to find that our path planner is able to find the shortest path, so that to ensure that our robots are efficient in their motion. And so on the topic of shortest path, there's a very famous algorithm, which we'll be talking about next, which is called Dijkstra's algorithm. And so Dijkstra's algorithm is a way of ensuring that our path planner produces the shortest possible path when performing graph search. So to start talking about Dijkstra's algorithm, let's first look back at our search algorithm template, and let's once again consider what we would have to change within this template in order to implement Dijkstra's shortest path algorithm. So highlighted on this slide are the key lines of pseudocode that would have to be changed in order to implement the Dijkstra's algorithm. And so similar to breadth first search, Dijkstra's algorithm will use a queue data structure to represent the visit list. But the key distinction between breadth first search and Dijkstra's algorithm is that Dijkstra's algorithm will use what's referred to as a priority queue. So within the main loop of the search algorithm, when the algorithm chooses to visit the current node, you can see on the line of pseudocode just below the while loop, it chooses the current node based on this priority of the minimum distance, with respect to the visit queue. And so this minimum distance is referring to the distance traveled from the start node to the particular node within the visit queue. And so based on that prioritization, Dijkstra's algorithm will choose which node it should visit next. And this then is how Dijkstra's algorithm will be distinct from breadth first search, and also how Dijkstra's algorithm will ensure that it finds the shortest path within the graph. So to walk through this, let's consider this graph in the lower right hand side just as an example, where let's say that the start node is denoted by the orange circle within the graph, And initially then it considers the two adjacent nodes highlighted with the blue color to be the initial visit queue. And so in this particular case, the distance associated with each of the two adjacent nodes to the start node are 5 and 8 as drawn on those two nodes. And so once again, that distance is with respect to the start node, and it's calculated shown as the based on the edge cost from the start node to the node highlighted in orange currently, and from the start node to the other adjacent node of the start node, which has a edge length of 8. So at this next step then, Dijkstra's algorithm would choose to expand the neighbor node of the start node, which had the minimum distance, which in this case is distance 5. So based on that, shown in this current slide, the visitation has occurred. So we've expanded now to what's denoted here as the orange circle. And now we consider the visit list, which in this case is a queue, to be the 3 potential nodes all highlighted with the blue, adjacent to the current node. And so once again, then drawn above each of these nodes is the calculation of the distance associated with each of the nodes. So you can see, so moving from the top of those 3 down to the bottom, there's a distance of 5 plus 1, so 6, 5 plus 6, which is 11, and then 8 being greater than 5 plus 2, so the distance of that lower node will get updated to be 7. So at the next step here, you can see we've now expanded to the adjacent node of our previously visited node, which again had the minimum distance traveled thus far. And so once again, Dijkstra's algorithm will iterate through the visit queue to update the distances of those nodes in the visit queue, and then once again expand based on the node with the minimum distance, which in this iteration of the algorithm was that node towards the bottom was 7, and it'll sort of iterate through this process until eventually it reaches the goal node, as it did in this particular step. And so again, at the conclusion of Dijkstra's algorithm, it would be able to return not only the path that reaches the goal node, but also the expected distance, which with Dijkstra's algorithm is guaranteed to be the minimum possible distance for traversing from the start position to the goal position. All right. And so the next question we could ask is, if you implement Dijkstra's algorithm in our 2D robotic planning framework, what would the performance look like? How would it compare to the algorithms that we've seen so far? And so to answer that question, so here's an example of an implementation of Dijkstra's shortest path algorithm within the search canvas. And so you can see it is similar to breadth first search, with slight differences, primarily in some of the trajectories are a little bit sort of smoother, but it is quite similar to the breadth first search results that we saw before. So in particular, here's an example of these two performances side by side. And so an interesting question that I would sort of pose to you that you should maybe think about when you're thinking through these algorithms is why the sort of visit pattern between these two is so similar. What kind of structurally within the pseudocode, within that template, could lead to the similar kind of visual performance that we see. But having said that, then one other question on the topic of kind of efficiency or finding shortest paths that we could ask is, Dijkstra's algorithm here is visiting many nodes that it might not need to be visiting, right? So all of the gray squares indicate the nodes within the search graph that were considered during and were visited during the search. And so it would be kind of beneficial for our robot if we didn't have to search as many of those nodes, because it would make our planning process more efficient, so faster. And so it turns out that the A-star algorithm, which we'll look at next, addresses that issue of number of nodes being visited. And so if you're curious, the original research paper where A star was proposed is cited here. So it comes from 1968 from a group of researchers at Stanford, actually. And this was a few years, I think it was within a decade after Dijkstra's algorithm was proposed. But if you're curious, here's the paper for A star search. It is interesting, so I recommend you take a look at it if you're curious. But if we kind of move forward, so let's look at how we would go from Dijkstra's algorithm to A star, because the two are very similar, with sort of the key distinction being how the two prioritize nodes to be visited. So if we modify this algorithm template to implement A star, here is the key distinction. So the first distinction is with respect to the priority queue. So instead of the priority queue considering the minimum distance traveled thus far within the search graph, instead the nodes within the visit queue are prioritized with respect to this F score. And so this F score then you can see is highlighted down below, the calculation of it, where it incorporates not only the distance traveled along the current path back to the start, which is what Dijkstra's was relying on, but you can see it also adds this line distance from the neighbor node to the goal node. And so this line distance is referred to as the H score. The distance along the current path of the neighbor node back to the start node is referred to as the G score. And together these form the F score. And so this line distance is what's referred to as a heuristic function. And so the heuristic function ultimately is what will sort of be advantageous for A star in reducing the total amount of work or the total number of nodes that are visited within the search. And so one other point that I'll emphasize here about A star is that the priority queue for A star will be implemented in Project 1 as a minimum binary heap data structure. So coming up towards the end of this lecture, we'll go into some details about how this minimum binary heap can be implemented. And so just to sort of highlight visually why A star is advantageous over some of the other algorithms that we've talked about today. So in particular, it visits less nodes, and so in this particular case, in this particular search canvas, if we compare, for example, A star, which uses that heuristic we were talking about, with Dijkstra's algorithm, you can see there's a very drastic difference in the total number of nodes within the search graph that have to be visited. So once again, as highlighted in these gray, as the gray squares, A star searches far fewer graph node positions than Dijkstra's does, leading to ultimately more efficient path planning. And so that's really the key advantage of A star for the purposes of our robots, right? Is that we want our robots to be able to calculate these plans very efficiently. And so that means the algorithms should be considering sort of as few operations as possible, or sort of expanding as few nodes as possible, while still ensuring that the algorithm finds the shortest possible path, which A star does guarantee. So the question then of how is it possible that A star can visit so few nodes while ensuring that the resulting path is still the shortest possible path? Well, A star, the way that it does this is by using what's referred to as an admissible heuristic when it during its estimation of the cost from nodes to expand to the goal node. And so back within the algorithm is where the admissible heuristic is actually implemented. So in particular, the heuristic function was the H score within the pseudocode. So this was the straight line distance from the node that's considered for expansion to the goal node. And so here on this slide you can see the definitions for admissible and consistent, which A star requires for its performance to be guaranteed. And so here's an illustration of the heuristic function for your consideration. The other thing that another resource that I'll point out on a proof of the admissible heuristic guarantees for A star can be found at this link here. And if you're curious, we can go into more details, more discussion of this during the interactive sessions. If you're interested, or during office hours. Okay, so given these algorithms, the next thing that we're going to talk about is going to be beneficial for your implementations on Project 1. And so this is the data structures that you'll be using to actually implement the A star search algorithm. And so namely, this is going to be a binary heap in order to implement a priority queue. So if we look back at the A star algorithm pseudocode here, you might remember just from a few slides ago we looked at the visit queue as being kind of the key data structure that the algorithm relies on as it's performing the graph search. And so this line in particular that's highlighted in red is the step in which the current node is basically decided on for expansion or for visitation. And so the way that the current node is decided on is based on that prioritization of the F-score, right? And so it decided to expand the current node based on whichever node from the visit queue had the minimum F-score. And so in order to find that minimum that node with the minimum F-score efficiently, we're going to be using a minimum binary heap data structure. And so these next set of slides are really meant to be beneficial and helpful as you implement this binary heap data structure. So for those of you maybe who haven't worked with binary heaps before, so a heap is a tree-based data structure that satisfies what's called the heap property. So the heap property specifies that within the data structure, so within the tree, every element has to be greater than all of its children in the case of a max heap. And in the case of a minimum heap data structure, every element within the tree has to be less than the value of all of its children. And so when we say then a binary heap, we're referring to the trees which have only up to 2 children. Or I should say the trees where all of the nodes within the tree have up to 2 children, but no more. So on the figure on the lower half of the slide, the left-hand side is illustrating a max heap. So once again, in a max heap, you can see that every element within the tree is larger in value than all of its children, right? So the root of the tree is 100. Its 2 children are 19 and 36. 100 is greater than 19 and 36. And if you kind of were to continue down that process, you could verify that the heap property of that tree is satisfied. Whereas on the right-hand side of the figure, we have a minimum binary heap, where again, in this case, we could look at the root node and see it has value 1, whereas each of its children has values 2 and 3. So in this case, the minimum heap property is satisfied, and you could work your way down and verify that the minimum heap property is satisfied for all of the nodes in this valid minimum heap. Okay, so in terms of how to implement this in software and in JavaScript, one approach which I recommend you use for Project 1 is to implement the heap as an array. So on this slide, we're illustrating graphically how the tree structure can be sort of flattened into an array, which you could implement as a JavaScript array. And so the key detail then for this implementation is how you manage your indexing to ensure that your indexing into the array essentially kind of treats the data structure as if it were a tree. And so I'd recommend you refer back to this slide for some of the details of some useful indexing calculations as you work on your implementations. So once again, so just to visualize in this particular case, here's sort of a layout of how the tree could be directly flattened and expressed into an array. So in this version of the heap, the root node is expressed at the start of the array, and then its 2 children directly follow, right? So in positions 1 and 2 of the array, you have the children element 5 and 3. And then sort of this process of representing the sort of next node's children follows as the flattening operation. And so using this representation, you should be successful with project 1. But as you have questions, feel free to post on Slack or to come to office hours, or during the interactive sessions we can discuss sort of one-on-one and make sure that this representation is clear. Okay, so using this representation, we talked about 2 key operations that we have to be able to support for our priority queue, which again, our priority queue is going to be implemented using this binary heap. So those 2 operations were enqueue for inserting an element and dequeue for removing an element. So let's handle the first one. So how do we insert a new heap element into a heap? So on this next slide here, so let's illustrate what the steps are for heap insertion. So let's say that we have this new element with a value of 15, and we want to insert it onto the current heap as shown on the right-hand side as a tree. So the process is, first, we add the new element to the end of the tree. So to the very end position of the tree, we insert this new element. Right, so once we've done that, we've effectively broken our heap temporarily, right? So the second step of the heap insertion is to check if the heap condition is satisfied. If it's not satisfied, which in this case it's not, then we're going to swap the inserted node with its parent, right? And so this is sort of an attempt to fix the broken heap condition, which we broke when we inserted the element at the end of the tree. So in this case, we did break the heap condition because 15 is greater than 8. So in this case, it's a max heap. So the max heap condition should be satisfied, but it's not. So we swap 8 with 15. So we swap 8 with the newly inserted element. All right. The process then kind of repeats. So until the heap condition is satisfied, you continually swap the inserted element with its parent. So in this particular case, once again, node 15 is greater than its parent, 11. So the heap condition for the overall tree is not met. So we're going to swap 15 with 11, which will then result in the tree shown in the bottom right-hand side of this slide. And at this point now, the heap condition is satisfied. So if you check every node in this tree with its children, you'll see that every node is greater than all of its children. And so we successfully inserted the element. Okay, so the next operation then we said that we need to be able to implement for our priority queue is the ability to extract elements from the heap data structure. And so to do that, let's look at an example. So the first operation for extracting the elements, so we're going to focus on extracting the root elements. And so the reason for that is that so you might remember that in the priority queue framework, right, when you're removing an element, you're always removing the element that has essentially the sort of the minimum priority or the maximum priority. And so in the case of a heap data structure, the root element is guaranteed to be either the sort of minimum priority element or the maximum priority element, depending on whether we've implemented a minimum heap or a maximum heap. So in this case, we have here a maximum heap. So if we extract the root element, we're going to be extracting this number 11, right? So we have the node with number 11 extracted, and then we have this empty root now within the heap. And so the operation then proceeds as we fill that empty root element with the last element in the heap. So in this case, the last element in the heap is that node with value 4. So we simply remove it from the last position, place it at the node, and then similar to the insert operation, we continually swap this element at the root that we inserted from the last position with its children until the heap condition has been satisfied. So in this particular case, so we placed element with value 4 at the root, and then we check and realize that, well, element 4 was actually less than its children at position 8, with value 8. So we then swap those two, and then can check and see that the heap condition is satisfied. In this case, the max heap condition. So we would be done. And so that's the process for extraction. Okay, so a few final thoughts for today's lecture. So one thought. So on this slide here, we've got a few things that I think are worth considering as you reflect back on today's lecture. And so these will be good discussion topics for office hours or during the interactive session. But I recommend you sort of look through these through these questions that we have and consider how they might be relevant to some of the material that we talked about, but also to your project. And so you can see, so for example, the first one I think is rather interesting, right? So how many operations from a computational theory point of view would be needed for heap insertion and extraction? So that's an interesting one. Another one would be, towards the bottom, looking at these different measures of distance, and to sort of ask yourself whether the choice of distance measure could be both a metric and also admissible, as based on the definition that we saw during our discussion on A star. All right, so then the last kind of concluding thoughts here. So just a reminder, so Project 1 2D path planning has been released. So in this project, we're going to be implementing the A star algorithm for search in a 2D world. And so within this implementation, we'll be relying on a heap data structure for the priority queue. And so the insertion and extraction operations will be implemented as part of the project. And so this will be implemented within JavaScript, and your code should be submitted through GitHub. So if you have any questions on GitHub or JavaScript and how to sort of work through this project, feel free to reach out over office hours or during the interactive session. I'll mention that last Friday's lab, our first lab, did cover Git. And so if you have questions, that might be a first resource. But don't hesitate to reach out over Slack or during office hours. We're happy to help as you get started on the project. And one final then thing I want to mention is that our upcoming lecture, our third lecture, will be a tutorial on JavaScript and HTML. So during this lecture, we'll go over some JavaScript basics to sort of help orient you for Project 1, and then also spend some time going over the workflow for Project 1. So we'll highlight kind of key portions of the code, what to expect as you're implementing the algorithms, and just some other helpful pointers to hopefully get you started. So thank you for watching this lecture, and I look forward to seeing you this week.